A great day of Red Hat Research Day. My name is Or Neuchmann, and I'm a senior cloud consultant here at Red Hat. With me is Ilya. One quick note before we start: you are talking right now with two guys with Russian background, Hebrew native tongue, and we're going to speak in English. So I want to thank you in advance for your patience. With me, as I said before, Ilya. Ilya, I want you to present yourself and tell us a little bit about what we're going to talk today.
Hello, everybody. My name is Ilya Korchinsky, and I'm a research scientist at Red Hat and Technion, Israel Institute of Technology. And we're here right now to talk about data processing, and more specifically about how we did it in the past, how we're doing it right now, what we expect to happen in the future, and most importantly, why should we at all care, and what value can this provide to us and to our customers?
So, Ilya, what is exactly data stream processing?
Well, so the question and the exact definition of what data processing is has evolved over time. So, for example, if you were to ask anyone like 20 years ago what data processing is, I believe most people would think about simple, plain DB, a single database that holds the entire information of your organization. It sits somewhere in your network. All the data is in the same format, manually inserted, manually preprocessed. And whenever you need some processing to be done on your data, you just go to the database, you write an SQL query, and then the DB does its magic, and you have your results. But unfortunately, for this simple paradigm of data processing, this model soon proved extremely non-scalable. And it happened as soon as we started actually using computers in all aspects of our daily lives. And contrary to some forecasts from the 80s and the 90s, now there is a computer in every home, and we heavily use the internet and social networks. And of course, we require much more than 600 kilobytes of memory. And what happened next, as a direct consequence of it, is that we started to generate lots of data. And I'm not only talking here about sheer volume of the data, but also about the speed, the velocity with which we produce data, and the variety, the heterogeneity of the data. Like in the beginning of the computer systems, we could think about numbers, strings, documents as our data. But today, all of a sudden, a movie is also our data, and a video game is data, and an audio file is data. We consider more and more things as data. And every new data type, of course, requires some dedicated kind of treatment. So to put it all together, we generate today much more data that we can simply put in one place, analyze, process, and return. So to address this new problem, a new wave of technologies have emerged, which is collectively known as big data technologies. Now, big data, besides, except for being an overused buzzword, it is also an umbrella term encompassing a lot of different strategies for processing huge amounts of data. All of these strategies are based basically on distributed processing, where we divide all of our data into small chunks, batches of manageable size that we can handle. And then we produce it in parallel on some distributed architecture. And then we somehow efficiently merge the results to produce the final deliverable. And there are a lot of big data technologies, systems that provide such functionality. Some of them, like Hadoop, focus on distributed data processing, style MapReduce, and some of them, like Ceph, focus more on distributed data storage without a single point of failure. But the common denominator of all of these technologies is that basically they allow us to overcome this scalability issue of having a lot of data and putting it all into a single DB.
So if I look at data processing today, why do you think it's not enough?
Well, I mean, big data technologies are amazingly efficient if you want to analyze historical data. If you want to run some offline analytics or periodical analytics that do not require the answer to be provided as soon as possible. But as soon as we think about real-time applications, here the problem starts. And when I say real-time applications, I mean all those time-critical systems where response time matters the most. Now, this is not something new, of course, and the real-time applications have been with us since a long time ago in systems like, for example, autopilot systems in airplanes or manufacturing systems in factories and plants. But recently, a number of new trends have emerged that caused a huge explosion in the demand for real-time applications. And we've seen them grow by a few orders of magnitude. And the first such trend which I want to address is, of course, the Internet of Things, or IoT. Now, with Internet of Things, now every small device suddenly can produce a lot of data and send me a lot of data for analysis. And every small device is suddenly a consumer and can consume some data and asks me to do some computation, which can be very complex. And all of these small devices, of course, produce a bigger picture of extremely complex applications that need to be handled in real time. For example, you can think of smart cities, monitoring smart cities, for example. And we have a very similar situation with 5G, where as mobile technologies advance more and more, on the one hand, the applications that we use become more and more complicated and require more sophisticated computations. And on the other hand, the mobile users become less and less patient. And they are not ready anymore to suffer any delay in their application. So we need to provide them the results of these extremely complex computations as soon as possible, because otherwise they close the application and they go on. Now, both with 5G and with Internet of Things, there is this recent trend called edge computing, where we basically bring the computation closer to the client to eliminate the network delay, or at least to significantly reduce it. But by doing so, we also significantly limit the computational resources that are available for doing the computation. Like edge computing runs, of course, on small embedded devices. And not only we need to, like I said, execute these complex computations with as small response time as possible, but now we also have limited resources, mostly limited memory. How do we proceed with it? How can we manage to still provide high quality of service like that? And of course, it is impossible to maintain this conversation without mentioning distributed AI and machine learning, because as we know, over time, there are more and more smart components and learning components everywhere. And machine learning technologies are extremely hot right now. But they are also a very difficult customer, let's call it that way, for data processing technologies, because it is extremely resource consuming and time consuming to run machine learning algorithms, especially when we're talking about training deep neural networks. So to briefly summarize all that I said, while in the past, most of the data that we were required to process was long-term data that doesn't change much over time, and only a small fraction of the data was really short-term, now we have significantly more short-term data that we need to address. And we believe that the trend will continue well into the future, where the majority of everything we need to process is the short-term data, which is generated right here, right now, and has a very small window of relevance. And if we don't process it right now, it becomes irrelevant anymore, and we don't need it. And only a relatively small quantity of the data will remain long-term, as we know it now. So we need a new kind of solution.
That's very interesting. So following the examples you just presented, just to do a small recap, we're actually talking about, on one hand, the time to live of the data is actually gotten shorter, but on the other hand, the data sources have actually increased significantly. So thinking about it in a data processing perspective, can the traditional data processing that we currently have today can handle those types of new challenges?
Well, the short answer is no, it cannot. So what basically happens today with most of these time-critical applications is that we just don't have the time and the capacity to process all this huge wave of data that we have. Our systems are overwhelmed by this data to the degree that we have to just throw away the majority of this data and only use a sample that we can handle and hope that this sample is sufficient for us to provide high quality results of the original computation. And that said, I want to introduce to you a relatively new paradigm for data processing that at least attempts to overcome these obstacles. And this paradigm is called data stream processing. And basically, with data stream processing systems, you don't have any intermediate storage except for maybe a very small one. You just have your processing components. You receive heterogeneous data from all the possible data sources, and your clients that consume the results are also heterogeneous. There could be human users or programming interface or whatever. The processing is performed per data item. So basically any object that you receive triggers a computation, or at least can trigger a computation. For those of you who think immediately about publish-subscribe systems, just a quick note. Actually, publish-subscribe systems are a predecessor to data stream processing systems, so it's all connected eventually. One important thing to mention about data stream processing systems. Data stream processing is an umbrella term that covers many individual solutions, algorithms, and methods for solving individual problems in real time by processing the stream on the fly. There is no single solution or a silver bullet for all the possible streaming problems, of course. Now, in addition, data stream processing is not only about solving these specific problems, but also about the overall architecture and how the different components of the system should be organized for it to perform well. And before we go into further details on stream processing, I just want to show right here that this paradigm is actually very natural to the way our brain works, because if you think about it, most of the time our brain works in a stream processing way, right? So we see something and we immediately react. We hear something and we immediately react right here, right now. We don't wait for some internal buffer to fill in and to overflow before we start processing this entire buffer. Of course, we're also capable of doing long-term data processing like DBs do. We have long-term memories and we can analyze those memories, but most of the time, like over 99% of the time, we really use our brains as stream processors. So it's only natural for our computing systems to behave similar. It is also important to mention that the same way as processing latency and response time is important in computer systems, it is also important for us, for our brains. That is the very reason why, for example, during driving, we maintain safe distance from the car in front of us, so that our brain has sufficient time to analyze the situation if the car in front of us suddenly stops. In a similar way, response time is extremely important, and this is what we want mainly to minimize in stream processing systems.
Well, the human mind is very interesting, to say the least. But I think maybe it's time to get into a little more practical example on where data streaming processes can actually be even more effective to the systems that we have today.
Sure, Oren, and we'll start by looking at a fairly basic example of a problem that has already been solved a long time ago. So in this problem, we have a cluster of servers, physical or virtual, it doesn't really matter. And we have the entry point, which is located on some embedded component. This entry point receives requests from our users and handles the load balancing and redirects these requests to the servers. Now, in this problem, we would like to identify the top 10 most frequent users, which means the users that connect most to our network. The complex aspect of this problem is that we have, say, 100,000 different users, but we only have enough memory to maintain 100 counters on this embedded component. Now, the trivial way to identify the most frequent users is to maintain a counter for each individual user in some sort of DB, table, and then to sort these counters and to retrieve the top 10 or top whatever the number that we want. Unfortunately, here we just don't have enough memory on this switch to hold all the information that we need in order to solve this problem. And again, of course, the simple solution is to connect the DB, but then we have this huge I/O delay of connecting to the DB and retrieving the answer. So the question is, how do you solve this problem? How exactly can you maintain information about the number of appearances of each user when you only have 100 counters and you have 100,000 users? And unfortunately, I don't have an opportunity during this presentation to get into further details on that. But the solution has to do with approximation algorithms and probabilistic guarantees, and it does not produce the correct result all the time. It is fairly easy to prove that you cannot produce an accurate result all the time, but in practice, it works quite well in a variety of applications. And we're talking here about a problem that was solved in the academic research over 15 years ago. And now we continue to a more real-life example, and also one that is connected to Reddit, what we are doing. And let's take a look at Kubernetes. What we have in Kubernetes is that we have this component called the API server that receives requests from clients and connects to a DB, or more precisely a key-value store called etcd, and fetches the data from it that assists it in making scheduling decisions. Now, of course, every time we have a new request, we have to connect to this DB, and this introduces a huge I/O delay because of all this storage that is involved. But what if we could just eliminate this DB and instead maintain a small and concise summary of all the information that we require in the process memory of the API server? This way, similarly to the previous example, it will be possible to speed up the process very significantly. And of course, it will produce great value to our customers.
Well, you know, that data stream processing sounds very interesting, but so how come we didn't hear about it in any places until today?
Well, so first of all, there are quite a lot of vendors of stream processing methods, including some of the major players like IBM, Google, Amazon, and many more that I didn't put here in this picture. And there are also open source libraries that support stream processing, such as Spark, Flink, and Storm. But the real answer to your question is twofold. First of all, we only now start to realize the potential of stream processing systems. Like, I mean, this area exists in academic papers since the 90s, I believe. But only now we have really enough use cases and large-scale use cases, as I exemplified before with IoT, 5G, and so on, to actually apply this technology for practical use and to make it mainstream. And in addition, this is still a developing area, and there are still many open issues that must be addressed before we actually make it the mainstream technology. To give you a single example, if you look at the internal structure of streaming workloads in some of these systems that I just shown you in the previous slide, you can see that a streaming workload is composed of a network of simple operators that have to be put together and connected to form an individual workload for each individual use case. And today, the users mostly have to create these networks by themselves. So they need to learn how to work with a particular system they are using. And they need to invest a lot of effort and time into creating robust and sophisticated networks of operators that handle their computation. And while it really works in practice, it is not too scalable to really large-scale applications. And I believe that as soon as we have automatic tools that can at least facilitate the creation of these networks, we will see a rise in the usages of these technologies. In addition to this problem of configuring and fine-tuning these networks, there are also additional challenges that stand between us before we make this stream processing future a reality. For example, we need to learn to adapt better to changes that happen on the fly as our stream processing system runs. I'm talking about, for example, changes in the distribution of the input data or changes in resource availability. We have more servers, less servers, and so on. We also need to learn to scale better to really complex computations, highly stateful computations that we know to handle them today, but we don't know to handle them using low resources, being low on resources. And in addition, there is also this problem of missing data and imprecise data. This problem is extremely relevant because, for example, in the IoT case, we receive our data from a lot of small sensors. These sensors are far from perfect. They can malfunction, and they can produce inaccurate results. And sometimes they don't return anything at all for some time. And we need to still be able to satisfy high quality of service, even if we miss some data or the data is uncertain to some degree. And and as a research scientist in the field of stream processing, my goal is to devise efficient and practical solutions to these and many other challenges before we make this dream come true and before we make stream processing the mainstream technology as it should be.
You know, Ilya, I took a little liberty in advance and I Googled data stream processing, and I hit a lot of results about CEP. Can you please explain to me and to the audience what CEP is and how is it connected to data stream processing?
Yeah, sure. So CEP, which stands for complex event processing, is often used interchangeably with stream processing. People use them as synonyms, while in fact, stream processing refers to any possible computation which we perform on streams, while complex event processing is about a very specific kind of streaming computation. And what we mean by complex event processing is basically detecting patterns of basic items or events in our data streams. So in this toy example right here, we have three streams of data that receive readings from temperature sensor, a humidity sensor, and the pressure sensor. And our pattern stays the following. We want to identify a situation where all three sensors report abnormal results, which exceed some predefined thresholds. And then, if it happens, we want to raise an alert. So basically, in very simple, primitive terms, we can say that CEP is executing SQL queries on streaming data. Now, we can think of a lot of relevant use cases for such a technology. Just to name a few. In smart cities, we can use CEP to analyze readings of traffic cameras, to identify car accidents, traffic jams, congestions, violations of traffic rules, and so on. In stock markets, we can identify all kinds of complex patterns for rises and drops in stock prices. If we're talking about cybersecurity, every behavioral signature of malware is a CEP pattern, because what a behavioral signature says basically is that if this happens and this happens and this happens, if an application connects to this IP and opens this file and I don't know what, then we want to raise an alert. So it's just CEP, and we can think of many other applications such as credit card fraud detection and many others. Now, as I mentioned before, we can look at CEP as running SQL on streaming data, but it is a very simplistic picture. In reality, CEP is much more than that, because if we imagine our stream as an actual river, then running SQL on stream is like fishing with a net. You throw the net and you invest a lot of effort into pushing it outside, and then you go on and sort everything that you get into your net, and you throw away the stones and all the junk that you have, and you leave only the actual fish that you wanted. Now with CEP, you don't need all this effort. CEP is more like fishing with a fishing rod, where you just pull the fish that you need and not anything else that you're not interested in.
Ilya, our producer just pinged me with a very important question. Do you even like fishing?
Well, to be honest with you, it's not my kind of thing. Because to be a good fisherman, you need a lot of patience. And I'm really bad at waiting for things to happen. So
yeah, I can relate. Perfect, thank you.
Yeah, now to make this explanation a little bit more technical and formal, if we want to run SQL on streaming data, what we have to do is basically to divide our data into batches, overlapping, not overlapping, it doesn't matter, to pull every time an entire batch into our DB engine, to run SQL on it, and only then we have our results. Of course, there is huge latency here as compared to doing it seamlessly with CEP, where immediately as a new item enters our system, we know with relatively small latency which are the previously arrived items it relates to, and whether we should or shouldn't return it as a pattern match together with these other items. Now, I don't have time right now to go into the internals of CEP, but it is not based on any technology similar to what DBs are based on. It contains complex state machines and advanced data structures, which I can make an entire talk about. So let's just omit it for now. And let's take a look at a real life example taken from what Red Hat actually do. So here we have this component called Elasticsearch, which receives a stream of system logs. and does very complex processing to these system logs. And then we have a GUI tool called Kibana to visualize the results of this processing. Now, Kibana actually visualizes and shows to the users a very small fraction of all the data received by Elasticsearch. So what if we could replace Elasticsearch with a CP engine that, instead of pushing all this data to some kind of intermediate storage and analyzing it later, just knows to detect the relevant data to isolate it from this huge stream of data. And then we could make Kibana work immediately with the CP engine and to display to the users this retrieved data that is received using CP technologies. Of course, it would result in a huge improvement performance-wise. And this is just a lone example. Now, similarly to what we have with stream processing technologies, we also have quite a few vendors of CP functionality, including, again, some commercial systems such as IBM Streams and open source libraries such as Esper or Flink.
You know, speaking on open source, I was wondering, are you personally involved with any open source project revolving around CP and data stream processing?
Well, yeah, speaking of CP engines, I'm involved in the development of what is called OpenCP. OpenCP is the next generation CP engine, which is based on novel cutting-edge research. Actually, most of the algorithms here are the algorithms that I devised during my PhD studies. And it can potentially achieve an improvement of several orders of magnitude over existing CP technologies due to these algorithms. OpenCP is now in advanced stages of development. So if you want to contribute to this effort or to become a user of this new engine, please contact us offline. Now, that said, I'm moving to the last major topic that we will cover today, which is the topic of streamlining. Now, as I mentioned before, everybody is digging the machine learning today, and machine learning is this thing nowadays. And of course, the question is, why can't we run machine learning algorithms on our streams? Why can't we get some advanced insights and learn things about our streams at runtime? And there are a lot of interesting things that we can do with our data streams, similarly to what we do today to stationary databases, such as stream classification, where we divide the stream into substreams according to some predefined list of categories, or regression, or detecting anomalies in our stream, or maybe identifying frequent patterns that occur in our stream, maybe for subsequently using these patterns for CAP. Forecasting is a particularly interesting example because it is tailor-made for streams. In the forecasting problem, we examine our currently available data, and our goal is to predict what will come next, what is going to be the next data item, or the next 5 minutes or 5 hours or whatever of data items that we will get. And to show you one specific example where this can be beneficial, let's take a look at Prometheus, which is a tool that pulls metrics from a Kubernetes cluster and then sends these metrics to Grafana, which is a GUI tool that this provides us the status of the Kubernetes cluster. Now, what if we had in parallel with this Prometheus forecasting component that looks at the same data available right now and shows us via Grafana how our cluster will look like in the next hour or the next day or the next week or whatever, assuming that the current trends continue. And we believe that could be beneficial for our customers in many cases. Now, that said, machine learning in streams and stream mining is exceptionally hard. It is much more difficult than traditional machine learning There are a few reasons for it, and I will only discuss the major reason here. So with traditional machine learning, you have this strict separation into the learning stage and the testing stage, where first of all you learn and then you apply your knowledge on newly seen data. So if I learn somehow that 1 + 1 = 2, I just can go on and apply this knowledge on anything. I don't need to learn anything new about it. Now with streams, the data is continuous and the learning process is also continuous. And our picture of the world should evolve as we see more and more data, and we have to do the learning stage and the testing stage all the time in a continuous way. And similarly to the case with the map of the Earth, in the past, maybe some of us thought that that the Earth is located on the backs of 3 elephants, and now then we had to reevaluate this knowledge and to forget it. The exact same situation happens with machine learning in streams, where we constantly learn new things and forget. In many cases, we only want to get the results on the newly available data, and not on the entire data that we have seen since the initialization of the system. This makes machine learning in streams exceptionally hard. And again, like I said before, as a stream mining practitioner and researcher, my goal is to target all these problems and to make machine learning in streams feasible in diverse scenarios. This is a very new, relatively new area. So there are not a lot of stream mining libraries, but some are still available today. And I guess that's it regarding stream mining. I will briefly summarize our talk before we move to the questions. So probably the main idea that I wanted to provide here in this presentation is that over time, we have more and more short-term data, and our applications grow more and more complex. And analyzing this short-term data within its short window of relevance, when we don't have enough available resources and want to do it with low latency, and our computation is complex, it's very challenging. And data stream processing is a promising avenue to addressing this problem. There is still much work to be done, and I strongly advise you to start utilizing data stream processing in your products now, and not only when it really becomes mainstream, which it undoubtedly will become in the future. So thank you, and I'll be happy to accept questions.
Wow, yeah, that first of all, I want to thank you in advance for a really amazing presentation. I want to give a chance to our people who are listening to ask questions. So feel free to do it in the stage tab. And until you do, Ilya, if that's okay with you, I have a few questions on my own. One thing, looking at everything that we just talked about from a developer perspective, one very interesting question comes to mind is, do I, as a developer, have some obligations to think differently about the client-server communication, or can I just work as normal as I do today and easily adapt the data streaming processing?
Well, basically, I believe that the basic model shouldn't change too much, if at all. Like, what stream processing provides you is better performance, lower latency, better resource utilization. But the main interfaces remain the same, which is, of course, good for us because it means that it should be quite easy to utilize a stream processing solution.
Okay, that sounds fair. Looking at the world today, and I'm talking about the IT world, obviously, where do you think will be a good place to start adopting data stream processing and all of its capabilities?
Well, Oren, I would expect you to tell me what is a good place to start, because from my standpoint, stream processing has a lot of applications, and you can take any of the examples that I provided during the presentation, or any other similar or not so similar use case and just start from it. And most of the time it would work.
Well, if you redirected the question to me, I think the example you gave today are a very good example of where to start. If we're looking at our monitoring systems and our metering systems, I think that we can get a lot of great value from data stream processing. So if anyone wants to know, I think that would be a great place to start it. We do have a question from our audience, by the way. The question is more specifically around edge computing, and if we want to do that stream processing under the edge itself. So I think I see chat that already responded in a partial answer that the data stream processing shouldn't be in the edge part, but mostly on the centric data center where we have a lot of more compute resource. Do you want to expand on that question or give an example of libraries or something that we can use on the edge devices, or centric is pretty much the straight answer?
Well, I believe you put it nicely. Maybe I should read the question to better relate to it, but your answer sounds fair.
The question is pretty straightforward. Is what are the modern libraries and toolkits for stream processing for the edge devices? But like I said before,
so there is nothing I'm personally aware of that is specifically oriented at edge computing, but the very principle of stream processing is to minimize the memory consumption. So everything that does stream processing is oriented at edge computing.
Okay, cool. So I hear a lot of news recently, and especially Linux news, obviously. And I know that the U.S. space program currently has adopted the Linux operating system to join their Mars expedition. Do you think it's a good place for the stream machine learning to be adopted as well?
Well, we just mentioned edge computing. And I think that running computation in space is the classic case, maybe the best possible use case for using edge computing, because you, of course, want to minimize any connection to Earth. So you want to do as much as possible on the edge. And consequently, it is a classic use case for stream processing.
Okay,
so, yeah.
Thank you. I like the answer. I think we don't have any more questions from the audience currently. Ilya, I want to thank you again. That was an amazing presentation. I really enjoyed it. And in general, I want to thank you personally because I really enjoyed preparing everything and setting up everything. It was a wonderful experience. I really like to thank our audience for being with us today. It was quite an adventure. And we'll hope to see you soon on the next Resource Day. So thank you, everyone. Have a great day. Have a great afternoon wherever you are in the world. And we'll see you soon. Thank you, Ilya.
Thank you. And thank you for coming and joining us today.